Welcome to another video on the igetChem channel, where we help you learn chemistry the easy way by showing you how to solve problems. If you have found some of our videos helpful in helping you learn chemistry, please do subscribe to our channel to help support our work. Today's video is on solving for the concentrations of a weak acid solution. So let's take a look at the problem. Calculate the concentrations of all dissolved species in a 1.00 molar solution of oxalic acid. And oxalic acid is a diprotic acid with Ka1 equals to 6.5 times 10 to the minus 2 and Ka2 equals to 6.1 times 10 to the minus 5. Okay, let's take a look at the solution. So the problem tells you oxalic acid is a diprotic acid. So instead of writing out the entire formula for oxalic acid, we will just represent it by this formula H2X. The reason why I put a 2 there is because I know oxalic acid, as the problem says, is a diprotic acid, so it has 2 protons to deliver, and so I'm going to represent it as H2X. In the first dissociation step, H2X will deliver a proton to H2O, making it H3O plus, and itself becoming the corresponding conjugate base, which is HX minus. The problem gives you the Ka1. Let me write that down. So Ka1 for the first dissociation step is 6.5 times 10 to the minus 2. So I'm going to write down the second dissociation step, but I will skip to the next page because I need a little bit of room on the first page to do the math associated with the first dissociation equilibrium. For the second dissociation, I'm going to take HX minus, which is the product from the first dissociation step. I'm going to use that as the acid in the second dissociation step. So acting as an acid, HX minus will deliver a proton to H2O, making that H3O plus, and itself becoming X2 minus. And the Ka2 that's given by the problem is equal to 6.1 times 10 to the minus 5. So in this problem, I have a 1 molar solution of oxalic acid. So I want to calculate the concentration of everything that I would find at equilibrium in the solution. So we'll start with a 1 molar solution of that. So this involves a fairly simple IC calculation. But before I do the calculation, let me just say the first step has a equilibrium constant that is about 10 to the minus 2. And for concentrations, that's about 1 molar. 10 to the minus 2 is really not small enough for us to be able to use the 5% rule approximation. So you know that some special treatment is necessary for the first dissociation step. And when you look at the second dissociation step, that one is 10 to the minus 5. So that one is definitely small enough for the 5% rule to apply. So, but let me explain what I mean. So I'm going to set up the IC table. So I have 3 lines as usual in the table. The first line is I for initial. The second line is C for change. And the third line is E for equilibrium. Okay, so I'm going to draw 4 columns, one for each species in the equation. As usual, the column with H2O is irrelevant because H2O is a pure solvent and it has no concentration changes throughout the reaction. So we will put down the equilibrium, the initial concentration for H2X. This is 1.00 and 0 and 0 to begin with. And for the changes, we can just look at the direction of the equilibrium. The equilibrium is going to move to the right because I started with no products. So all the changes on the right side would have positive signs, and all the changes on the left side would be minus, but there's only one of them. So now you can use the stoichiometric coefficient from the equation. So you see this is 1, 1, and 1 for every one. So you just put down 1x, 1x, and 1x for all of them. And now applying the changes to the initial, you can write down the equilibrium concentrations in terms of the unknown x. So that's that. And now you can write that back into the equilibrium expression. So writing down the equilibrium expression, Ka1 is equal to the H3O plus concentration multiplied by the Hx concentration divided by the H2X concentration. So as I've said in some of the other videos, if you have many equilibria at the same time in the same acid-base solution, they all share H3O plus and OH minus and H2O with each other. In this case, this is a diprotic acid, so there are two equilibria. I'm going to indicate them by writing down number 1 for this one, and then this one is number 2. So in this case, there are two acid-base reactions going on, and they share H3O plus and OH minus and H2O molecules with the autoionization equilibrium of water. So they are related to each other. But in the case of these acid-base calculations where you have multiple equilibria going on, you will always just use the one with the strongest K value to determine the H3O plus concentration, and that one will set the concentration for H3O plus for all of the other equilibria. In this case, obviously, the first one has a stronger Ka because that's 6.5 times 10 to the minus 2, while the second one is only 6.1 times 10 to the minus 5. So we will assume that the first equilibrium will set the H3O plus concentration. So we can just use that to calculate H3O plus. Now putting in all of the unknowns that we have, so we have x, and in the bottom we have 1.00 minus x. So clearly you can just set up a quadratic equation, and you can then solve it with the quadratic formula. In this video, because I've shown a number of different problems using the quadratic formula, so just for variations in this video, I will show another method that you can use to solve these equilibrium problems without using the quadratic formula, because the quadratic formula sometimes can be quite long. I've said at the beginning that this value for Ka, right there, is not quite small enough for an approximation to be used. And the approximation that would actually apply when Ka is small enough is to assume that the change x is very small compared to the initial, and then the denominator in this case is just approximately about 1. So we said this approximation that we would use if Ka is small enough is really not good enough, because you will find if I use this to actually calculate a value of x, x is not within 5% of 1. But let's assume that that is true. So let's assume that we can use the approximation. And if we do that, we would have an estimate for how large this value of x is. So we will assume, in fact, that 1.00 minus x is just roughly equals to 1. And if we make that assumption, then we can go and finish the calculation without using the quadratic formula, because the first step will give me 6.5 times 10 to the minus 2 equals to x squared divided by just 1, because 1 minus x is approximately equal to 1. And now if you take that equation, you can easily solve for x by taking the square root of 6.5 times 10 to the minus 12 times 1.00. And if you do that, you would find an approximate value for x. So if you do that, x turns out to be equal to 0.255. And let me just call that solution 1. The reason is because that will turn out not to be the right solution, because that is assuming an approximation that we know is actually not correct. So how do I know that this approximation of assuming that x 1.00 minus x equals to 1 is not correct? Well, the answer that I got by using that approximation is x equals to 0.255. And 0.255 is certainly not smaller than 5% of 1. So this really isn't a good enough approximation. But what we can do is to start with that approximation and now use that as the approximate answer for x, and then you can then arrive at another, perhaps better approximation for x. So let me demonstrate how that goes. Now, using this value x equals to 0.255, then the value 1.00 minus x becomes 0.745. And now if you put that into the equation right there, you will find that now you have a second equation, which is 6.5. Let me use the same color as the one above. So in this case, this will come out to be 6.5 times 10 to the minus 2 is equal to x squared, but now instead of dividing by 1, it's divided by 0.745, because that's the value of 1 minus x. And then you can use that value to arrive at a more accurate value for x. So x is just the square root of 6.5 times 10 to the minus 2 multiplied by 0.745. And if you put that into your calculator, x will come out to be 0.220. I'll call that solution 2 because that might not be good enough, but we can check. So what you can do is that what you can see is that now between the first and the second solution is slightly different from the first one, and the second solution will be a more accurate approximation to the correct answer for x. So what we will do is just basically continue this process until we see x doesn't change anymore, and then at that point x will be the correct answer. So what we are saying is that as we do this, x will become closer and closer to the right answer, and so using this so-called successive approximation, you will get to a better and better answer. So if you take x equals to 0.220, subtract that from 1, you will get 0.780. And now you can put that back into the equilibrium expression. So 6.5 times 10 to the minus 2 now is equal to x squared divided by 0.780. And so in this case, the 0.780 is obtained from right there. And now with that, you have solution number 3. So x equals to so you can take the square root of 6.5 times 10 to the minus 2 multiplied by 0.780, and x will turn out to be equal to 0.225. And so that's solution number 3. And so now you see between solution 2 and 3, the answer changes, by only about 0.005. And you see that as you repeat this more and more, you will get out a better and better solution. In this case, we are actually already close enough, so I can take that as a good enough approximation. But you can check by going another step. If you follow exactly what I have done in the first two steps, you will find that the next approximation will turn out to be equal to 0.224. So at that point, the value of x will not change anymore. So we see in this case, the correct answer is 0.224. If you had stopped at step number 3, that would have been essentially the same, close enough. So that gives us the value for x. Okay, so going back into the IC table, you see that the value of x is equal to the H3O plus concentration. So this is 0.224 molar for the H plus concentration, and 0.224 molar for the HX minus concentration. And then for the H2X concentration, 1 minus 0.224 will give you 0.776. So these are the concentrations for the sum of the species in the solution. So that's for H2X, that is for H3O plus, and that is for HX minus. So we've got the solutions for those. So let me just put a box around them. So finally, there's one more that we need to deal with, because we also have to deal with the second dissociation equilibrium. But to just remind you of what we said earlier, we are going to assume that the reaction with the largest K will drive the equilibrium and set the H3O plus concentration in the solution. So even though the second reaction will generate an additional amount of H3O plus, that's not going to be significant compared to the amount of H3O plus coming from the first reaction. So the H3O plus concentration is set. Okay, so we have the H3O plus concentration from there. Now let's look at what is in the rest of this equation. So in the rest of this second dissociation equilibrium, not only do we have H3O plus, we also have HX minus, which is on the left side of the second dissociation step. But you see that HX minus is actually on the right side of the first dissociation step, and the first calculation, in fact, has given me the value of HX minus. So I can simply read off these two concentrations from the solution to the first part of the problem, and let me put those down. So this one is 0.224 molar for H plus, and for HX minus is also 0.224 molar. And now those can go into the Ka2 value. The equilibrium expression is Ka2 equals to H3O plus X2 minus times X2 minus divided by HX minus, and that is equal to this value 6.1 times 10 to the minus 5. And now we have the two values that we know. We have the HX minus and we have the H3O plus. Each of them is equal to 0.224. And so the only unknown in this equation is the concentration of X minus, is this one. So let me write that. And of course, that is equal to 6.1 times 10 to the minus 5. You see, in fact, these are the same, so they cancel. So what that would do is to immediately give you the X2 minus concentration, which is 6.1 times 10 to the minus 5 molar. Okay, so that is the end of the problem. Now we have calculated the concentrations of everything that are ionic species and dissolved species in the equilibrium. Okay, so just to recap, if you have a acid-base calculation with more than one acid-base equilibrium, you will use the one that is the strongest Ka to set the H3O plus concentration in the solution, and all the other equilibria will then comply with that H3O plus. And you see that with that, the second equilibrium becomes really easy to solve because we already know the H3O plus concentration for the second equilibrium. And just one more thing, in this problem, we have, instead of using the quadratic equation, we have used this method called a successive approximation. And sometimes you find this to be a little easier. If you want to use the quadratic equation to solve this problem, you will get the same answer. And if you want to watch some of the other videos we have on our channel using the quadratic equation, I'll make some links to some of this video.